Hello again, and welcome back to another episode of the CCQTA Lunch and Learn series. I'm Dave Murray, Secretary of the CCQTA and Principal Consultant at Omnicon Consultants. This episode will focus on insoluble solids in crude oil, otherwise referred to as filterable solids. Before we get to filterable solids, let's go back to basics and talk about sediment and water. Then we'll chat about the impacts of solids and why they're problematic, and then move on to filterable solids test methods, and then lastly, have a look at a few case studies that illustrate real scenarios where solids have caused issues. Sediment and water, or S&W, is commonly performed in both the field and in the laboratory, and is the most common quality specification for crude oils. In most of North America, the S&W specification is 0.5% by volume. Now let's take a little closer look at S&W. The S&W test uses a centrifuge to separate oil, water, and solids, or sediment, based on their density. Solids are the most dense, so they go to the bottom of the centrifuge tube. Water is next in the middle, and lastly, oil is the least dense, so it ends up at the top. Each phase is measured using the volumetric scale on the tube, and the results are reported as percent by volume. Pretty easy, right? The centrifuge tube image here is pretty common, with a little bit of solids at the bottom, almost too small to measure, and then water and then oil. In this case, the S&W is actually greater than 0.5%, so it's actually off spec. The solids are typically larger particles, so say greater than 10 micrometers, and include sands, salts, and/or corrosion products with little affinity for either the oil or the water. What I want to highlight with this first image is that the S&W is intended primarily for water, with solids making up a small component of the S&W, not the other way around. If this crude contained 0.5% solids, the impact to pipelines and refineries would be severe. Now let's look at the same tube under UV light. Under UV, another phase is revealed between the water and the oil. We call this a mid-phase. This emulsified phase contains waxes, asphaltenes, resins, and yep, you get it, more solids. The solids in this phase are typically fine minerals and clays less than 10 microns, which have strong emulsion stabilizing tendencies. These are really the solids that cause refiners the most trouble. These solids are also not accounted for in the typical S&W because they're not visible as part of the test. So why are solids a problem? Firstly, and probably most importantly, solids can't be turned into finished product, so they're simply a waste stream that refiners and producers have to deal with. If you're an operating pipeline, then deposition is your major concern. Where this deposition happens determines what kind of problem it causes. When solids deposit in the pipeline, there's a significant risk of corrosion under that deposit. The solids form a nice environment to trap water and provide an environment for chemistry and bacteria to work away at the pipe wall. To mitigate this risk, pipelines put extensive pigging and maintenance programs in place. Solids also make their way into instrumentations, valves, pump seals, all resulting in shortened lifespans and potential equipment failures. Next, crudes that pass through intermediate or long-term storage tanks will deposit solids in that tank through settling. Over time, these solids build up, and eventually those tanks will need to be taken out of service for cleaning. Typically, tanks have a 20-year inspection and cleaning cycle, so excess solids can result in tanks being taken out of service way early, which is very disruptive and very costly. If you're a refiner receiving the crude, solids cause several issues. The most acute problem is upsets to the desalter because it quickly impacts crude processing and throughput. Upsets typically occur when an emulsion layer forms at the oil-water interface. An emulsion layer can build up with little indication that it's forming until the desalter is already in an upset condition. This emulsion either carries over or carries under. When it carries over with the crude, water and solids are carried into the preheat system and crude tower, where solids deposit in a heat exchanger, trays, piping, and even impact finished product quality. Similar to a pipeline, anywhere deposition happens, there's an opportunity for corrosion. When it carries under with the desalter brine, oil reaches the wastewater treatment plant, which has to react quickly to maintain effluent quality. Lastly, even if the desalter is not upset, approximately 50% of the solids still travel to both the crude preheat and tower, and the remaining 50% to wastewater treatment plant. At the end of the day, solids are a considerable factor in many unplanned shutdowns, resulting in lost production and significant cost to refiners. Solids in the desalted crude really don't have a good place or product to go to, other than possibly heavier streams such as asphalt, heavy fuel oils, and coker feed. There are, however, limits to the permissible solids content in these streams. Asphalt quality can be impacted by solids. Marine heavy fuel oil has a limit on aluminum and silicon content. And coker heater fouling and flash drum foaming have been reported, and those producing anode coke are very concerned about solids contamination. Some of these smaller crude solids will also be present in distilled fractions. Here the concern becomes exchanger and heater fouling and catalyst poisoning in hydrotreaters, hydrocrackers, and fluid catalytic cracking units. So now that we know what kind of problems solids cause, that begs the question as to how much is okay and how much is too much. Like I said earlier, 0.5% is most definitely too much. And just for reference, 0.5% equates to 5,000 parts per million, which would totally throw a desalter for a loop. Since the S&W method does not do a good job of quantifying solids, another method has to be used. ASTM D4807 is the most common method used for solids in crude and condensate. It's a relatively simple filtration method used to quantify toluene insoluble solids, otherwise referred to as filterable solids. Let me summarize the method quickly. A sample of crude is dissolved in 90 degrees C toluene, and then the mixture is vacuum filtered through a 0.45 micron filter. The residue is rinsed with additional hot toluene, then dried and weighed to get the mass ppm of filterable solids. Because the method uses hot toluene, any waxes, asphaltenes, and resins are dissolved, leaving only the toluene insoluble solids. These may be sands, salts, clays, corrosion products, and insoluble organics such as polymers. The Industry Technical Committee, through Crude Monitor, has been testing for filterable solids since 2012, so they've amassed a large amount of data on a wide variety of pipeline quality streams. Trans Mountain has also been collecting filterable solids data for many years as part of their product quality program. This chart contains 2,600 combined data points provided by both. Solids range from less than 1 part per million to a maximum of 940 parts per million. The average for this large data set is 180 with a median of 203 weight ppm. The plus minus 1 standard deviation shows statistically where 68% of the results lie. The black line shows a plus 2 standard deviations where 95% of the results lie. Now we have a good idea of what typical filterable solids are in transit, so now we need to know what refiners are seeing on their end. This chart shows the data refiners have collected on the crude feed to the refinery over the past 5 years. When we compare the refinery data to the pipeline data, we find they're actually quite similar. The average refinery values are slightly lower, likely due to loss in pipeline transport, for all the reasons we kind of talked about earlier. Now let's put a little bit of scale to this data. At an average of 50% desalter efficiency, that means about 98 weight ppm is going to the crude unit, with another 98 weight ppm going to the wastewater treatment plant. Now that probably doesn't sound like too much, so let's scale that a little bit more. Assuming a 100,000 barrel a day refinery, that means 2 tons of solids go through the refinery every day. Refiners seem to be able to handle that without any problems. What they can't handle are rapid excursions in the solids content. For a refiner, a steady, predictable feed is ideal. Now let's consider the maximum values we saw in the pipeline data was 940 ppm, and what that translates to at the refinery. Now the refiner that is used to 2 tons a day must process 10 tons a day. This typically also happens with little to low notice, though there's really no way for them to prepare for the resulting upset. So now we know that refiners see solids averaging approximately 200 weight ppm each day, and for the most part, these do not cause issues in the refinery. We asked refiners and several on-site additive suppliers what solids level in crude would be deemed problematic. Most don't have hard correlation data, but the group's consensus was that 150 to 300 weight ppm is tolerable. Greater than 300 ppm is problematic. Note that some refiners did comment based on their experience that 300 weight ppm is too high for their plant. Regardless, the average daily filterable solids content of 200 weight ppm, calculated from the historical data, appears to be in the tolerable range. With all the solids information that I presented so far, the CCQTA discussed recommending a pipeline specification on filterable solids to avoid excursion levels that cause issues for refiners. At the time, a 300 ppm filterable solids limit was discussed. However, midstream companies felt that it may be burdensome to feeders. On further discussion, refiners indicated that soluble salts should not be included as part of the filterable solids since they dissolve into the salt or wash water and are not responsible for fouling. CCQTA worked with Agate and Bureau Veritas to develop a modification to D4807 to see how much of the filterable solids was water-soluble salts. This chart shows the mixed sweet and sour filterable solids data with and without the water-soluble salts. The gray bars are the insoluble solids, while the orange bars are the water-soluble salts. In only 2 cases did the total filterable solids exceed 300 weight ppm, and with the soluble salts removed, none of the samples were even close to the initially proposed 300 weight ppm limit. At this point, the CCQTA is simply in a data collection and evaluation phase while we determine if any specs should be proposed, and if so, what value would be appropriate for production through refining. The next question that surfaces, are some types of solids worse than others? Well, it turns out that size matters as well as the properties of the solids. Large diameter solids, say greater than 2 microns, is where you'll find sands, salts, and corrosion products. These are the most likely to settle in tanks and be removed during desalting. Small diameter solids, say less than 2 microns, are primarily clays. They're not easily separated by gravity and they're very surface active, meaning they tend to bind with complex structures like asphaltenes and resins. This means they also tend to stabilize emulsion, so they reside in the emulsion layer and will not settle. When stabilized emulsions are present, they also tend to trap the larger diameter solids. Within these groups separated by size, there is another group called TIOMs, or toluene insoluble organic material. These are organic in composition but insoluble in toluene and in many cases in any other organic solvent. These TIOMs could fall into either size range depending on their properties. They include insoluble polymers. These could be the result of reactions of other products to form polymers, or they could be in their native form. Asphaltenes bound with surface active clays. Both clays and asphaltenes are planar in shape and form layers. When clays are found between asphaltene layers, the resulting combination is no longer soluble in virtually any organic solvent. Kerogen is a highly reduced form of carbon that has limited hydrogen and is nearing the composition of coal. Graphite has recently been found in several crude tower deposits. It's commonly used as a friction reducer in horizontal drilling and fracturing operations. Since it's simply a crystalline form of carbon, it's also insoluble in organic solvents. When D4807 was initially published in 1988, filtration would reveal deposits composed primarily of inorganic materials. However, over the last 25 years, CCQTA members have consistently also identified TIOMs on their filters. These are often found using thermal gravimetric testing of the filter solids. TIOMs will decompose under high temperatures with and without oxygen present, leaving only inorganic solids behind. Evidence has also been collected through CCQTA project that TIOMs contribute to equipment fouling and plant operability issues. As part of the CCQTA's work, and with the assistance of Bureau Veritas and Agate Laboratories, a modified version of D4807 was developed. This modified method allows for the quantitation of both toluene and water-insoluble solids, with the difference between the two being the water-soluble salts. The modified method also provides recommendations for additional testing that could be performed on recovered solids to provide further characterization. This method is available publicly on the CCQTA website under the Publications tab. I summarized the D4807 method earlier, but I didn't really get into the finer details. However, the modifications to the method are as follows. The filter material has been changed from nylon to PVDF, which allows both toluene and water to be used as a filtration solvent. Next, the filtration and solvent temperature has been reduced slightly from 90 degrees C to 85 degrees C to accommodate limitations in the PVDF filter. The purpose of the elevated temperature is to ensure any wax crystals are liquefied, allowing them to pass through the filter, so this minor temperature change should have a negligible impact. Next, a hot water wash has been added after the toluene wash to remove water-soluble salts. Then additional weighing steps were added to allow quantitation of both the toluene and water-insoluble solids. Lastly, the modified method has been separated into two procedures. Procedure A provides total toluene and water-insoluble solids, but does not differentiate between the two. Procedure B speciates the toluene-insoluble, water-insoluble, and water-soluble solids. Effectively, Procedure A skips the extra weighing steps and just washes with toluene and then water and weighs the final solids. This is intended as an expedited method where the speciation is not required unless a problem is identified. Now let's look at some case studies on asphalt quality, refinery coker operations, and exchanger fouling. These help demonstrate how solids can impact refinery operations. Let's start with asphalt quality. This case study is over 30 years old and occurred during a period when communication between producers and refiners was poor. A heavy oil producer wanted to reuse produced water, which required that the water be cleaned prior to reuse. Two options were being explored. One involved installing mechanical filtration equipment, which necessitated significant investments in the equipment, including a process for disposal of the recovered oily solids. The second option involved the injection of a high molecular weight cationic polymer in a dissolved air flotation unit on the water stream, which would then redirect solids and oil waste back into the produced crude. The chemical option was selected since it was deemed more cost-effective and eliminated the need for solids disposal. At the time, this specific heavy crude was being purchased by a refiner for the purpose of asphalt production and had a good history as an asphalt crude. Suddenly, as it turns out, coincident with the implementation of the additive usage, problems surfaced during asphalt production, and the refinery became unable to meet required product specs. After a few frustrating months of searching for solutions, the refiner ceased buying the crude and replaced it with a new, less problematic feedstock. The details of this quality issue were not communicated to the producer until years later during a chance meeting with a third party familiar with the refinery issue. Next, we'll look at refinery coker operation. Some refineries operate with delayed cokers. These units are designed to process an asphalt-type material like vacuum tower bottoms to produce higher value products such as gasoline and diesel fuel. The thermal cracking process produces both the lighter fractions and coke. Within the refinery vernacular, delayed cokers are often referred to as garbage cans since their feed can include plant slops. The injection of slop into the coker feed, however, is usually limited by the quality of the slops and the type of coke being produced by the unit. This particular refinery produced shot coke, which is often a challenge to remove from coke drums. The refinery noted that incidents of hazardous coke drum eruptions were occurring during the coke boring and removal process that were linked to the solids content of the feed. That refinery now limits the crude feed solids to 150 weight parts per million, which roughly equates to 75 weight ppm or 25 pounds per thousand barrels on the desalted crude. The change has since minimized incidents of coke drum eruptions. Lastly, let me share a case study where production and refining worked together to change practices and resolve a problem. A member recently presented this case study to the CCQTA. They reported fouling in preheat exchangers in both their upgrader and refinery, which pointed to a potential feedstock issue. They could tie feedstock issues back to the production because it was their own production. They began an evaluation of a production facility directly upstream. The water from the separator went into a skim tank, and the slop oil from the skim tank was injected back into the sales oil going to the refinery. On testing, they found the slop oil contained a significant quantity of insoluble solids. For a period of time, they chose to stop injecting the slop and just see what happens. Shortly after the slop injection was stopped, the fouling at the refinery also stopped. That showed a direct correlation that the slop was likely responsible for the fouling. While it was a win for the refinery, it was very costly to truck away the material for disposal, so that wasn't a long-term solution. In the end, they chose to only inject the slop if it met the pipeline specification for S&W, and that seems to be keeping the fouling at a manageable level. It's a good cause and effect story because they were fully integrated and had control of both upstream and downstream. Therefore, operational change could be agreed on by both sides. It's also a cautionary tale for production slop handling, which may be one of the sources of high solids excursions we talked about earlier. Although slop may appear harmless because the volume is low relative to production, it may also have unintended consequences. As for the next steps in this project, the CCQTA will continue to work with pipelines and refiners to evaluate filterable solids and water-insoluble solids. We're also going to continue to seek refinery data on solids levels versus upsets and fouling so we can nail that down a little tighter. And lastly, as more data becomes available, we'll compile and report on the findings and, if necessary, recommend limits on solids. That's it for this episode. Thanks for watching, and I look forward to connecting again. If you'd like further information about this topic or any other topics the CCQTA is working on, please visit our website at ccqta.com. If you have any feedback, please send it to secretary@ccqta.com. Please check back regularly for new additions to our Lunch and Learn series and other videos.